I just hand over to you, and thank you.
Okay, thank you, Kaida. So can I just turn off my video?
Yeah.
Yeah, okay. Yeah, it's my pleasure to share with you my studies regarding color emotion. So today I'm going to talk about early studies in interior colors and lighting regarding color emotion. So can you turn to the next slide, please? Okay, so in this slide, you can see on the left-hand side several terms, including lightness, brightness, and so on. And these are the terms we have been interested in for scaling and quantification. And these are the scaling and quantification of human responses to colors. And if you look at the lists, and you can find some terms like naturalness, warmth, happiness, activity, liking and harmony. Next slide, please. And you can see that some of the terms belong to color appearance attributes. And these terms, such as lightness, brightness, and so on, can be found in the systems like CLab and CCAM16. Next slide, please. And on the other hand, you can also see the terms like naturalness, warmth, heaviness, and so on. And these are very different from the terms we just saw above. These are not normally called color appearance attributes because we don't use them for assessing color appearance. However, we can see several terms for these words, such as color meaning, color image, color emotion, or color semantics. Next slide, please. And in this presentation, I'm going to use the term color emotion to cover the words including naturalness, warmth, heaviness, activity, liking, and harmony. These are what I'm going to talk about in this presentation. Next slide, please. So the first question is, what is color emotion? Next slide, please. So an example is that the color, as you can see on the screen, well, it's a red color, right? And what does it feel for you? Does it feel warm or cool? Next slide, please. Another color you can see here is a yellow. And is it warm or is it cool? Next slide, please. According to my experience in several conferences, I have tested this so many times. And according to these experiences, I found most people will find the red color warm, and they will find the yellow color on the right-hand side just a little bit less. About 60% of them will see this color, yellow, as a warm color. Next slide, please. So color emotion is when we human see colors. As you can see on the bottom left. So we see colors and we have feelings. In the above, we can have feelings like warm, cool, clean, dirty, fresh, stale, heavy, light, hard, soft, active, passive, and so on. We can also use color measuring instruments to do measurement of the color, such as CS1000, CS2000, and other instruments, which can be used for color measurement, and we can convert the measurement data into a color space, such as CLab. And finally, we can create a bridge to connect the measurement data on the left-hand side and our feelings about warm, cool, clean, dirty, and so on. So we are actually breaking the gap by bridging the two sides. Next slide, please. So after we can do that, after we bridge the gap, we can do some predictions about color and our feelings, the association between the two sides, for applications such as interior design or fashion design. Next slide, please. Today, the outline of my presentation will be like this. First, I'm going to talk about some early studies of color emotion, which will be followed by universal models of color emotion for interior lighting, and I will talk about some future directions. Next slide, please. First, early studies on color emotion. Next slide, please. Before I'm talking about the color emotion, I need to talk about something about C-lab color space, because there will be some equations based on C-lab. So as you can see here, we normally use lightness, chroma, and hue. And lightness is denoted here as an L star, and the hue angle is HAB, as you can see in the bottom, and chroma is C star AB. Next slide, please. So when you look at the C-lab space from the top view, you can see something like this. You see two axes. The horizontal axis is called A star, which represents reddish to greenish. And the vertical axis is B star, representing yellowish to bluish. Next slide, please. If you have a color located here, next slide, please. And the chroma of that color is like the distance between the location, the coordinates of that color here and the origin. Next slide, please. And the hue angle is like this. So, we have from 0 degree to 360 degrees. And that's the hue angle. Next slide, please. Here are some literatures regarding color emotion. And in many of them, they use several color emotion scales, as you can see in the table. So here I would like to divide them into several underlying factors. The first one is called Hue Related Scales. Next slide, please. So as you can see, the hue related scales are something like warmth, warm-cool, color heat, temperature, and color heat. Well, it's very often used by researchers. So hue-related scales like warmth or temperature is very popular. Next slide, please. And according to the existing models in these papers, we found some equations of warm-cool. For example, in the year 2000, Sato and his co-workers developed a model like this. So the warm-cool can be quantified by the cosine of the hue angle and also the brightness in the equation. And Professor Shin and his co-workers in the year 2000 also developed equations for warm and cool. And myself in the year 2004 developed an equation for warm-cool, including the terms chroma and hue angle. And my equation is very similar to Sato et al.'s equation, as you can see in this slide. Next slide, please. So here it's very important to note that hue angle is a main factor for warm and cool. And also we can see the two models are in the form of hue difference formulae with reference to a reddish orange. So, hello? Hello? Can you still hear me?
Yes, yes.
Okay, right. So here I put 50 there because we found in our experimental results that 50 degrees in terms of hue angle is the warmest hue. So it's put there for this reason. Next slide, please. So I can illustrate that idea of warm-cool using this slide. So on the left-hand side, you can see a hue circle, and the warmest hue is actually a reddish orange. And any hue that's similar to that hue angle will feel warm as well. And if you look at the right-hand side, you can see another factors affecting warm-cool feeling, which is the chroma of the color. So if a color in a hue, which is a warm hue, for example, the orange, as you can see here, but if you increase the chroma of that hue, you can increase the feeling of warm. On the other hand, if a hue like blue here is a cool color, you can increase the feeling of cool by increasing the chroma of that hue. So that's a reason why we include chroma in the equation as well. Next slide, please. The next underlying factor is lightness-related scale. As you can see in this two tables, the lightness-related scales, including soft, hard, potency, color weight, potency again, color weight again, and color weight. Next slide, please. So basically, we think this is very important scale as well, and we chose heavy light to be the representative of the lightness-related scale. And it happens that several researchers also use this scale in their development of color motion equations. So Sato and his co-workers has the equation of heavy light using only one parameter, lightness, in the equation. As you can see here, heavy light in C lab equals minus 3.5 lightness plus 190. So heavy light, the feeling of heavy and the feeling of light of a color is related closely to lightness and to lightness only. It's very simple, right? So if you see the equation in the bottom that was developed by myself in the year 2004, it also has only one parameter, the lightness. But if you see the Shin and his co-workers' equations, it's a lot more complicated because they think that lightness is not the only factors that can affect heavy and light feelings. So they also included chroma and hue angle. Next slide, please. Next slide, please. But for me, I think heavier light feelings of a color is related to lightness only. Because according to my experimental data, I just didn't see that strong connection with the feeling of heavy and light to other dimensions of color. Next slide, please. The third underlying factors of color emotion is chroma-related scales. As you can see in these two tables again, the related scales to chroma include dynamism, clear grayish, activity, color activity, activity again, color impact, and color activity. Next slide, please. And we chose something like dynamic or active to represent this third factor of color emotion. So in the first equation developed by Sato et al., this is an equation of dynamic versus passive. So if we just simplify that equation, we can see it's actually a form of color difference. And if you see the third equation shown here in the bottom, this is also a very similar form of color difference with a reference color at chroma equals 0 and lightness value equals 50. Next slide, please. And next slide, please. And that can be illustrated by this graph. So in the middle of the color space, which is actually a medium gray, which is what we found the least active color or the most passive color among all other colors. So medium gray is the least active color, and any color that's located in C-lab space near that medium gray will feel passive as well. And any color that's located far away from medium gray in C-lab space, that will feel active. All right, next slide, please. So these are just basic findings we found about color emotion. And now I'm going to talk about factors affecting color emotion. Next slide, please. The first one is fashion style. Next slide, please. And I'm going to use this as an example, as a comparison between fashion styles. There are 3 styles to compare: spring, summer, and winter. So as you can see in the 3 graphs, spring means the style of that dress, and summer style, as you can see here, and the winter. Next slide, please. And we used 30 color combinations in these different styles of clothes. Next slide, please. And for summer, is this, and this is for winter. Next slide, please. And we used the computer display to do the experiment. So here is an example of a scale harmonious versus disharmonious. So if you find this graph, if you find the combination of color in this clothes harmonious, the observer will be asked to press a button according to his or her feelings. And if it feels harmonious, they may just press a button on the left-hand side, and the opposite will be go for the right. Next slide, please. And the scales used in this study includes fun, serious, trendy versus old-fashioned, young versus mature, like, dislike, and harmonious, disharmonious. Next slide, please. So again, just a reminder that we are going to compare between the 3 styles: spring, summer, and winter. Next slide, please. Okay, so here we are comparing different styles between the 3 seasons, as you can, as you have realized. So on the horizontal axis is one style, for example, spring, and the vertical axis is another style, for example, summer or winter. And here you can see the comparisons for British observers and the comparisons for Chinese observers. And please note that the Chinese observers are, at the time of the research, located, and they stay in the United Kingdom. So this study was carried out in the UK. So when I'm comparing the scale fun series, for example, if you look at the graph on the top left, it has the correlation coefficient of 0.89. And if you can see the scatter diagram, all the data points kind of feel a trend like a straight line, right? So that for me is a very high correlation between spring and summer styles for British observers. And if you look at the graphs for the top 3 graphs, you can see all of them have a high correlation between spring versus summer for the top left, between spring and winter, top middle, and between summer and winter, top right. However, if you look at the Chinese data, only the styles between summer and winter, the bottom right, seems to have a high correlation. Next slide, please. Now it's a result for trendy old-fashioned. And here we see very similar pattern as we saw previously for the fun series. So here you can see very high correlation for the results by British observers. And you can also see a very high correlation results for Chinese observers between spring and winter and between summer and winter, as you can see in bottom middle and bottom right. Next slide, please. For young, mature, the same pattern again. So you can see all high correlation between the three styles for British observers. But for Chinese observers, it's only high correlation only for the comparison between spring and winter and between summer and winter. Next slide, please. And this is very different result from like-dislike because you can see all the correlation coefficient, they are not very high. Not only for Chinese observers, but also for British observers. So this seems to indicate that the like-dislike seems to be influenced by the fashion style. Next slide, please. And also for harmonious disharmonious, the correlation coefficients are not very high. And as we know that color preference, which is represented here by like-dislike, has a very high correlation with color harmony. So we think this is quite a sensible result. Next slide, please. So that was a comparison between different styles, and the conclusion from that is color preference or like-dislike, and also color harmony can be affected by the fashion style. We just need to just bear in mind that. Then the next comparison is between different cultural backgrounds for color emotion. Next slide, please. And in this comparison, we used data from 8 regions in the world, including Argentina, Germany, Spain, France, Iran, Sweden, Taiwan, and the UK. Next slide, please. So this slide shows the comparisons between the 8 regions for the feelings of warm, cool. And here you can see so many dots. Each dot represents a color, I think it's color pair, not single colors. So as you can see that a correlation between different regions, for example, the top left is a comparison between, I think it's between, wow, it's very small letters, Taiwanese observers, and the vertical axis is British observers. Okay, so each graph in this slide is a comparison between the 8 regions. And as you can see, there's very similar patterns for these comparisons, which is very high correlation between any 2 regions in the study for warm and cool. So perhaps you will think, well, of course, because warm, cool feelings about color needs to be universal, right? Well, we think in this study that was the case. Next slide, please. For heavy light, again, we can see that pattern, a very high correlation between the 8 regions. So I think it's an even better trend here. The next slide, please. For active-passive, it's also a very high correlation between the 8 regions in the world in this study. Next slide, please. Now it's a result for like-dislike. As you can see here, the pattern is different. It's not like a very clear trend, like 45-degree straight line. In some cases, we found it's not like a straight line. For example, on the top right, which is a comparison between Swedish. Sorry for my eyes are my short side. It's Iranian and British. Oh yes, so it's a comparison between Iranian observers and British observers at the top right graph, and the correlation coefficient is 0.55. And very similar pattern can be found for some other comparisons in this slide. And some of them are just having very low correlation coefficient. For example, there is a 0.27 between Argentine and French observers, and 0.38 between Swedish and French observers. So that means, again, like-dislike will be affected by another factors called cultural backgrounds. Previously, we have mentioned that like-dislike can be affected by fashion style, and now like-dislike seems to be the only scale that can be affected by the cultural background. Next slide, please. So here just show the two very different patterns you see from the graphs in previous slides. On the left-hand side, it's a very high correlation between Iranian and British observers with a very high correlation coefficient, 0.89. On the right-hand side, between Swedish and French observers with a very low correlation coefficient, 0.38. So we think that the like-dislike can be affected by cultural backgrounds here. Next slide, please. The next is a comparison of color emotion between the two gender groups. Next slide, please. Here is experimental results from the 8 regions, as I mentioned previously. The 8 regions include in Argentina, the UK, French and Iranian, those 8 regions, and we just combine all the male observer data together, and we also combine all female observer data together, and we try to compare the two gender groups. So here you can see the result on the left-hand side. Here we just trying to look at whether the mean chroma of a color pair will have any impact on the score difference between male and female. Here we are calculating the scale, male minus female. So if that value is high, if it's as high as a positive value, that means male observers prefer that kind of mean chroma value. So on the left-hand side, we can see that male observers tended to prefer higher mean chroma colors than female observers. Or we can say, using a different way, perhaps we can say that female observers tended to prefer lower mean chroma color pairs. All right. On the right-hand side, we are trying to see whether the mean lightness of a color pair, whether this can influence the like-dislike feelings between the two gender groups. So as you can see here, the male observers tended to prefer lower mean lightness colors, and female observers tended to prefer higher lightness colors. So if we combine the two graphs together, we can get a very exciting conclusion. Next slide, please. So if we look at the color space like this, this is a PCCS. It's a tone system. And we can have different tones to be arranged according to their lightness and their chroma. So we can have a pale tone, the light tone, bright tone, and also vivid tone, and so on. And we can say that the light colors will be located on the higher position of this slide, and high chroma will be located on the right-hand side, and low chroma will be located on the left-hand side of this slide. Next slide, please. So previously, we say that male observers tended to prefer high chroma, low lightness, and the female observers tended to prefer high lightness, but low chroma colors. So if we look at that result using this tone system, it seems to be like male observers tended to prefer the colors on the bottom right tones, which is something like dark, dull, deep colors. But female observers seem to prefer color tones like pale colors, light grayish, or bright colors. So if you look at, or if you trying to find in your past experience, will this make sense to you? Next slide, please. And the next factor we are looking into about color emotion is context or application area. Next slide, please. Because we are talking about context or the application area, that means we would like to apply color emotion to different contexts. For example, the food such as cupcake, or the drink such as cocktail, or the clothing such as t-shirt for female and male, and also for housing. And we can do the color emotion to be applied to the interior design or the exterior. We can also apply color emotion to the car interior design or the exterior. Next slide, please. Here are the images we used in the study for cupcake and cocktail. So you can see we just apply different colors to these images. Next slide, please. And we also applied different various colors to the t-shirts for female and males, as you can see in here. Next slide, please. And for the interior and exterior of the house, as you can see here, different colors but the same image, different colors for the same house image. Next slide, please. And here are the images for the cars, inside and outside of the car. Next slide, please. And we are using computer display to show images. So here is an example of a scale like, dislike. Next slide, please. So here shows results for different scales. We used four, well, actually we used many. Warm, tense, hard, heavy, as you can see here. And for each scale, we have 8 context or 8 application areas. For example, if you look at the graph at top left, which is the result for warm. Okay, so that's a very interesting result. I almost forgot. So as you can see here, in that graph, on the top left, you can see 8 yellow dots. Each dot represents an application. For example, cocktail represented by number 1. And number 2 means car interior. Number 3 means car exteriors. So all the 8 yellow dots are located very close to each other in the graph of warm here. That means the observer, they agree quite well to each other regarding their feelings about warm color in cupcake and car interior and car exteriors and cocktail and so on. That means their feelings about warm of the colors in these applications are very similar. And that means perhaps the 8 different applications didn't really influence our feelings of warm color in the images. And if we look at the graphs, the other 3 graphs on the right hand side and in the bottom, we can also see very similar patterns. All the 8 dots in each graph all located very close to each other, right? Next slide, please. Well, as I said, we used many scales. I almost forgot how many scales, but here are just another the examples of results for scales: masculine, modern, clean, and active. And again, you can see all the dots in each graph are located very close to each other. And that means these scales was not affected by the 8 applications. Next slide, please. And here is a result for like-dislike. This is very different again for like-dislike, and because we have seen like-dislike being exceptional, strange, or perhaps it's not strange, but it has been affected by the fashion style and also affected by gender, right? Now it seems to be affected again by the different applications of color emotion. So you can see the pink dots in this graph are located not so close to each other, but some of them are located quite far away from each other. So this seems to indicate that the applications of color emotion for like-dislike would be influenced by that application. Next slide, please. So here just shown the sequence or the rank order of like-dislike for different applications. For example, if you look at the top, that's the rank order of like-dislike for cupcake. And the second row is the rank order for cocktail, and so on. I cannot go into the detail. So anyway, you can see the difference of the rank order for like-dislike, and that rank order will be different for different applications here. Next slide, please. So in conclusion, factors affecting color emotion here, including fashion style, cultural background, gender, and context of the application area. There seems to be only one scale here, which is like-dislike, that can be affected by these factors. And actually, like-dislike can be affected by all of these. But the other color emotion scales was not influenced by these kind of factors. So this is kind of good news to us because we know that color emotion, except for like-dislike, is independent from these factors. So we can do something more. Next slide, please. That something more means a set of universal models of color emotion, because we found that most color emotion scales will not be affected by cultural backgrounds. Next slide, please. So in this study, we use experimental results, experimental data from even more different regions across the world, including the 8 regions I just mentioned, and also we have Japanese data as well. We also have we also have Chinese data as well. So next slide, please. And all the color samples in this experimental data are here. So as you can see in these graphs, they are distributed quite widely in the CLab space. They kind of cover all the hue angle, as you can see on the left-hand side, and also they cover a variety of chroma levels and a variety levels of lightness, as you can see on the right-hand side. Next slide, please. Here is our results about warm-cool. So as you can see in these graphs, the warm-cool feelings about colors seems to be affected by hue angle, as you can see on the left-hand side, and also it can be affected by chroma, as you can see on the right-hand side of this slide. Next slide, please. And here we would like to use the approach of kind of a color difference formula to do the modeling of the color emotion in this study for the warm cool. Next slide, please. And in this study, we use this method to test whether the model is actually working or not. Because from our previous study, we found that there is a kind of additivity of color emotion. For example, if you know there are 90% of people will agree that the red is a warm color, but only 50% of people agree that the yellow is a warm color, then there will be 70% of people agree that the combination of the red and the yellow, when they're combined as a pair, would be a warm color pair. So that's a kind of average calculation of average for the color combination emotion. Next slide, please. And this kind of average method can be applied to 3 color combinations as well. But we are going to use only 2 color combinations for the test of the models for color emotion. Next slide, please. And we are using again this kind of scaling method. Next slide, please. And this is for color pair testing. Next slide, please. And the result for warm-cool, a new universal model has been developed by this. And again, there is Chroma there, there's hue angle there. Next slide, please. The next scale, heavy and light, is found to be affected by lightness only, as you can see in the middle graph. Next slide, please. So the model for heavy and light is rather simple. It's just a function of lightness, as you can see here. Next slide, please. The third scale used in this study is active-passive. As you can see, it's effective only by chroma. It seems to be affected only by chroma. That's interesting. Next slide, please. Because actually, according to our previous study, active-passive is not only affected by chroma, but it's kind of affected by a color difference between the color we're looking at and a reference color, which is normally a medium gray. And in this case, this reference color is a little bit yellowish medium gray. Next slide, please. And we are using the additivity theory to test our model in terms of correlation coefficient. And we can see in this table that the equations used in this study show very good predictive performance, with a mean correlation coefficients of 0.85 for warm cool and 0.87 for heavy light and 0.89 for active passive. Next slide, please. Okay, so this is the last part of my presentation, color emotion for interior lighting. I'll try to finish my presentation in time. Okay, next slide, please. I'm going to share 2 studies. Next slide, please. So for the first study, we used a real space. Five minutes left in your meeting, really? I only have 5 minutes left. Okay, so the aims of this.
Never mind.
Okay, aims of the study. Thank you, Kaida. Is to understand the effect of a CCT, which is a correlated color temperature of the light source on color emotion responses. So this is a structure of that space. We have a space including a sofa, and also we have a table there. And a very important part of it is we have 3 colored walls. Next slide, please. In this study, we used 3 styles of light sources, A, B, and C. You may wonder what kind of lights they are. Next slide, please. Let's find out. So we used, well, because this was done about 10 years ago, and at that time we used several ways to change the colors of the three walls, and the first approach is use the curves. So it really didn't look like real walls, but we have tried. So next slide, please. Here shows the first style of lighting. So let's call that A light. So as you can see, we have 6 different color walls, and also we have 2 different color temperatures for the 8 lights. Next slide, please. And here shows the B light, and again we have 6 color walls and 2 color temperature. Next slide, please. This is a result for the C light. Next slide, please. As I mentioned, there are 2 correlated color temperatures used in this study. The first one is 2700 K. Next slide, please. The other is 6500 K. So the difference between the 2 the 2 CCTs are the one 2700 K is a little bit warm white, but the 6500 K is a little bit cool white. Next slide, please. So again, these are our experimental conditions for study 1. Next slide, please. We have 19 young adults as the observers, and female observers are a little bit more. Next slide, please. We used these scales in the study, including warm, cool, classical, modern, relaxed, tense, comfortable, uncomfortable, like, dislike, well, so many, elegant, inelegant, bright, dark, spacious, small, clean, dirty, harmonious against disharmonious. Next slide, please. So first, we use principal component analysis to divide these scales into 2 PCs. Next slide, please. And here are just the Pca results in the PC graph. Here shows the 2-dimensional space. As you can see, on the top is the scale bright. On the right-hand side, here shows the warm. Next slide, please. And of course, you can see the location of the other scales in this study. For example, spacious is very close to the scale bright. That means if we see an interior design and we see that bright, we find it bright, we may tend to also think it's spacious. Next slide, please. This is another another way of looking at the same data. So we just put all the data there, and we just used this to show you that the data can be divided roughly by the 2 color temperatures. Okay, so here is very interesting result for us. That means whatever wall colors, whatever the style of the light, color temperature is very important. And also brightness is another very important underlying factor. Next slide, please. Here I would like to show you our second study regarding color immersion in interior lighting. Next slide, please. This is the experimental room we used in this study. Next slide, please. We used different colored light sources in this room. Next slide, please. Next, please. Next, please. Next, please. Next, please. So as you can see, we just used the LED lights is a wall washer to do the lighting in that room, so we can create different various atmosphere in the room. And we used 30 observers, and they are all students in my university. Next slide, please. While we used 25 white lights in this study and also 15 colored lights, and I would like to explain in more detail about how we define these white lights and colored lights in the next slides. So next, please. This slide shows our white lights, excuse me, the 25 white lights. We just selected them using the U prime V prime diagram, and we used CCT against DUV values. Well, you know the meaning of CCT, which means the correlated color temperature, right? So the high CCT means cool white, the cool kind of cool feeling of white light, and the low CCT means it's a warm feelings of the white light. And what about DUV? DUV, and if you can see there is a DUV equals 0. If DUV value is 0, that means it's Planckian locus. And that means all the colors on that locus means neutral in theory. And if DUV is a positive value, that means it's a white light, but it's a little bit greenish white light. If DUV is a negative value, that means it's slightly purplish white light. Next slide, please. So here shows the 15 colored lights in this study. So we kind of use the color gamut of the LED lights, RGB here, and we just select the RGB, the full red, full green, and full blue from the LED lights. So that means R3, G3, and B3 in this graph. We also selected the colors less red. How to say that? The chroma value is lower than the full red, and also we have chosen the orange colors because we think orange colors are very important as well. So here we have reds, oranges. Is it oranges? No, it seems to be yellowish. No, sorry, it's yellows, greens, blues, and purples. Next slide, please. Next, please. Okay, so here shows, sorry, previous slide, please. Sorry, okay, so here shows the scales we used in this study. Because this study would like to investigate color immersion for rating the entire experimental room. And also we would like to use this experiment to rate the observer's face, because if we ask the observer to look at themselves via a mirror beside them, so they will have a mirror to look at. So they in the room, they look at the mirror in the room. If the lights changes, then they will realize that their face will change as well. They may they may find it more smooth or more natural or less natural. They may find their face younger or less young. They may find it more masculine or less masculine. In the top, they also can rate the room in terms of lighting, brightness, tension, and distance. Next slide, please. Here is just an experimental procedure for our experiments. So we just ask the observer to close the eyes and color adaptation, and also close the eye again. And then we do the color adaptation to the test light now. Then we ask them to do the rating for the room. And then we ask the observer to look at the mirror and rate their own face using the scales I introduced previously. Next slide, please. Here is the result for room impression. Next slide, please. And because I'm going to show you a lot of graphs in the next few slides, I need to explain in more details first. You will see very similar graphs like this. So I will show a kind of a histogram graphs with a horizontal axis, DUV value. And in the middle is DUV of 0. That means the colors is located on the Planckian locus. All right, that means it's a neutral color. And on the right hand side, it means the positive value for DUV. That means it's more and more greenish. On the left hand side here, that means more and more purplish because the DUV value is negative. Next slide, please. Here, I would like to show you the results for lighting, brightness, tension, and distance. Right? So the horizontal axis is all the DUV values. As you still can remember, the DUV, the middle of the horizontal axis is DUV of 0, right? And the left side means DUV of negative values. That means it's purplish white light. So on the top left graph, you can see that the observers tended to prefer the DUV value of negative values. That means they tend to prefer purplish white lights. And also on the top right graph, the observers tended to find the negative DUV lights. That means purplish white lights more bright. And for attention and distance, I think the results are not very significant. So, okay, so that's the data you can see here. You can compare yourself. Next slide, please. And the next part is a comparison between CCT. So perhaps you need to remember from the left to the right is from low to high CCT. And as the color of the bar the color of the bar shows, the left-hand side means it's a little bit yellowish white light, and the right-hand side means it's a little bit bluish white light or cool feelings of white light. Next slide, please. So according to the results, observers tended to prefer high CCT white light, and they find the high CCT white light brighter than low CCT white light. Next slide, please. And for the excitation purity of the light of the light source, here I would like to just again to show the left-hand side means the low purity and the right-hand side is high purity. Next slide, please. And here are just a very clear trend for lighting. So the observer tended to prefer low excitation purity of the white light. No, it's not white light. I think this is the colored light. And they find the high purity of the colored lights brighter. I think this makes sense because this is something to do with HK effect. The Helmholtz-Korach effect, because we used all the light sources of exactly the same luminance values. So they have the same reading from our luminance meter, but in our eyes, we don't feel the same brightness. We found a higher purity or higher saturation of the light, brighter. Next slide, please. Here is the graphs showing the distribution of the lights in the U prime V prime diagram. The result for lighting, as you can see here, in terms of bubbles and bubble charts, the bubble can represent the value of lighting. The bigger the bubble means the observers like the room better. They prefer the room better. Next slide, please. So according to this graph, it seems to be like the observers tend to prefer the colors located in the white color, the white light area, because all the bubbles in that area are bigger than the other areas. Next slide, please. If we zoom in to look at the white light area, we can see some differences between different white lights. As you can see here, the blue bubbles representing the high values for liking. So that means the observers tended to prefer those bubbles located in the bottom of this graph. Next slide, please. Here is the result for brightness. Next slide, please. And the pattern we found here is that the observers tend to find the colors located kind of in the blue or purple area. They find it brighter than the other areas. Next slide, please. If we look into the details of white lights, again, the observers tended to find the colors in the bottom area of this graph brighter. Next slide, please. This is the result for tension. Next slide, please. The observer tended to feel tense when the colors of the light has a high intensity in terms of a saturation of the color. Next slide, please. If we compare the tension feelings for the white lights, we again found that the colors on the edge of these graphs to be more tense. Next slide, please. The result for dizziness. Next slide, please. This trend is very similar to the tension, right? So the colors of high excitation purity will give you a high dizziness value. Next slide, please. This is very similar to the results of tension. The dizzy colors are located at the edge of this graph. Next slide, please. And of course, we can do a comparison between these different scales for the room rating. We found that the liking and tension will have a very high negative correlation. For example, that means if you find a room, a color light room, tense, you don't like it, right? Next slide, please. Here are showing the result for facial skin impression. Next slide, please. And again, we would like to look at the comparison between different DUV values for the scales. Next slide, please. So here for the observer's face, we are asking them the questions regarding naturalness, young, smooth, feminine, and liking. And the results, as you can see here, somehow they seems to be like more or less the same, but we still can see some trends. For example, they tended to be the highest value at negative DUV, but it cannot be the lowest DUV value. It's somewhere between DUV of 0 and a slightly lower small negative DUV value. Next slide, please. Now we would like to compare between CCT. Next slide, please. So for CCT, we think that the naturalness will have a high correlation with CCT because the observers found their face to be natural when they are in the room with a light source of a high CCT. Next slide, please. Now we would like to compare between the purity of the color. Next slide, please. So as you can see, a natural needs to be when you are staying in a room with a low purity of light source. And you can see the other results here as well, if you like. Next slide, please. Here shows the results for the scales for our facial impression. The first one is like dislike. Next slide, please. What we would like to, what we are most interested in is white lights, because sometimes, although sometimes we are using colored lights for interior lighting, but normally we are using white lights. So here is the result for white lights. And what kind of white lights are the most liked by the observers? As you can see here, the result is the high CCT, but negative values for the DUV. Next slide, please. Here are the results for natural against unnatural. Next slide, please. Again, we found that the observer found that high CCT with negative DUV values to be more natural. Next slide, please. Here are the results for smooth versus rough. Next slide, please. This is the result for the smooth result for white lights. I think the result is quite interesting, because we found that your face will feel more smooth if you are lit by a slightly purplish white light, because purplish white light has a negative DUV value. Next slide, please. Here are the results for young, old. Next slide, please. And again, purplish white light is very interesting, because it makes your face to feel more smooth and also make it feel younger. All right, so purplish white light is a good choice. Next slide, please. Masculine and feminine. Next slide, please. Yeah, this is masculine. Is it masculine? I'm not sure. I'm not sure about the validity of this graph. Sorry, let's just pass. Next slide, please. So here shows the correlation coefficient between these scales for facial expression. As you can see, the highest between these scales may be 0.96 between liking and natural. That means if you like the face in the mirror, you find it natural as well. Next slide, please. All right, so these are the results and the experimental findings we have so far regarding color motion applied to interior design. Now I would like to talk about something about the future directions of color motion. Next slide, please. So first, I think perhaps individual difference in color motion is interesting. By individual difference, I mean the personality. Personality is something difficult to study, but we think it's interesting. And the second direction is application-oriented studies of color emotion. We still think the applications can have an impact on color emotion. So perhaps we can do some more application-oriented studies for this. And the third direction, I think, is color emotion in virtual reality, because virtual reality is interesting. So perhaps you would like to do more research in the applications of virtual reality, and color emotion is one of them, right? And finally, I think artificial intelligence is important now. And perhaps there is chance that we can do some research into AI and creativity in color design. And how to do that, let's try. Okay, next slide, please. So that is my presentation.